This is section 5.5, part 3, which is 5.5 is exponential logarithmic models. So in this part 3, we're looking at a model that's already given to us. But this has to do with carbon dating. So when you want to figure out how old a piece of wood is, we have a thing called carbon dating, where it's basically looking at how much carbon is supposed to be in that object to begin with. And so one of the ways to do that is that if you have a piece of wood, when it gets cut down off of a tree or a tree gets cut down, there's a certain amount of carbon that is expected to be in a certain mass of that we know, that we can measure like right away as soon as that tree has died. And there's different types of carbon. So there's carbon 14 and carbon 12. And what we know is that the ratio of those two carbons, they decay at different rates. And so as you might have equal amounts of carbon 14 and carbon 12 to begin with, but as time goes on, maybe carbon 14 decays faster than carbon 12. And so based off of what ratio they have left with them, we can actually tell how old that piece of wood is just by measuring how much carbon 14 is in there compared to how much carbon 12 is left in there. And so for this particular piece of wood, somebody calculated that, and here is the ratio right here. And this formula allows you to take that ratio and substitute it into this formula and actually solve for what I'm looking for, which is the amount of time in years. So I get 1 over 9 to the 14th power equals 1 over 10 to the 12th power times e to the negative t over 8,223 power. So this is a formula that somebody else has already developed. They've already calculated this for us. So again, this now breaks down into just being a problem like other ones we've been dealing with in this class, where my variable is up at an exponent and I want to get it out of there. So before I get it out of the exponent, I need to get this exponential part by itself. So I'm going to multiply both sides by 10 to the 12th so I can get rid of this fraction that's here. So I'll have 10 to the 12th. Again, that's just a 1 with 12 zeros, so I'm not worried about that. 9 to the 14th power. It's going to be a really big number. Again, I'm not worried about that. I'll let the calculator do that in a little bit. Equals e to the negative t over 8,223 power. So now that I have this exponential part isolated, I can try to get this by itself. And so the technique we've used is you take that exponent, we're changing it from exponential form to logarithmic form. So that's the, in case you've forgotten, it's a base to the power equals n. You can change that into log base b of n is equal to the exponent, p. So I can change it from this form to this form. Right now this is in this form. My base is e. My exponent is negative t over 8,223. The n value here is just this ratio. So I'm just taking those pieces. I'm taking this, which is n. I'm taking this, which is p, and this, which is my base, and I'm just rearranging it so it looks like this. I just choose to do it backwards. So instead of doing this way, I do p equals log base b of n. It's the same thing. So I'm taking that exponent, I'm writing that down first. Equals log base b. Well, my base is e, so log base e, we have a special name for that, so that's natural log, of n, so the n is 10 to the 12th over 9 to the 14th. Again, that's just something I'm going to punch in my calculator eventually. But I want to get this t by itself, so I need to do two things. One, I need to get rid of this 8,223, which is in the denominator. But I also need to get rid of that negative. So I'm going to do both at the same time. I'll multiply by negative 8,223. That'll get rid of this in the denominator. It'll get rid of the negative sign. So all of this gets multiplied by negative 8,223. So those cancel, and I end up with t equals this. It's my exact answer. I can't do much with that. and then I approximate that answer, and it comes out to be, I mean, again, we're talking about something really old here, so I think it's appropriate to just round it to the nearest 1,000 years. So it's about 26,000 years is how old that would be. So again, that is how, one of the ways you can go through and calculate something like that. Now, the next problem. Find the exponential model, and it's telling me what my equation should look like. And I want it to fit this graph. So I've got lots of points, but I've given us 2 of them here. So anytime you're given an equation that you want to write, whether it's a quadratic equation, a linear equation, a cubic equation, whatever, if you're given some points, what you want to do is just start plugging those in. This is an x and a y. And so I could take these values and plug them in here. So I'm going to take 0, 5. And if I plug that in here, I would get 5 equals a times e. And then it would be b times x. So it would be b times 0. And I'm going to do the same thing with the other point, 4, 1. And I would get 1 equals a times e, and if I put a 4 in there for x, it'd be 4b for that power. So what I have is 2 equations with 2 variables. But in this case, this becomes just 1, because anything to the 0 power is 1. So this equation gives me a equals 5. So right now, I know that y equals 5e, and then I've got something times x. But I have to figure out what that something is that goes here for the b value. Well, that's where this comes into play. Now I'm going to take this value of 5 and plug that in here. So I get 1 equals 5 times e to the 4b power. Again, same old song and dance for us, guys. Our variable that I'm looking for is up in an exponent. So the first thing I do is try to get this whole exponential expression by itself. So I divide by 5 and I get 1/5 equals e to the 4b power. Then, because this is n, this is my base, and this is the p value for the power, I can rearrange that and I can get that 4b by itself by taking the natural log base e, of 1/5. So if I divide by 4, this is what I get. My b value ends up being the natural log of 1/5, or if you prefer 0.2, all over 4 times x. So this is my equation. And if you take that and you plug that equation into like a graphing calculator and you graph it, it will go through, it'll look just like this. It'll go through the 0.05 and it'll go through 4, 1.